Okay, I posed a question at the beginning because people are having trouble with the thermodynamic cycle uh, of that container sitting in a reservoir with a couple of valves in a tube. Just pick up on what we did last time, okay? So my question is the fundamental questions. Much heat energy has to go in. And how much potential energy change given gas volume, high temperature, low temperature, which for our example are 400 and 300 Kelvin. Given T high, T low, and the height of the upper reservoir. Now, class spent 10 minutes discussing it. And I sat down and joined the discussion for about 20 minutes to pull things a little further along. Okay? Everybody should have the information they need. Boils down to answering these questions. And I'm not going to say any more about it, but I did post a summary that I thought was posted late last week and it wasn't. And that was my fault. I will say that you can expect errors every once in a while because my HTML editor is being really obnoxious. Every time I try to save a change, it tells me you can't save it. And it makes me save it as, which exposes me to a disastrous error, causing me to have to back things up way too often, making the whole process more complicated than it ever has been or needs to be. Okay. So I got to be really careful, develop a whole new set of habits so I don't lose everything. And then I mentioned AI. This is worth, okay. Ask AI. First of all, I gave it a couple of lines of HTML and said, can you translate this to LaTeX? Boom, right away, beautiful, perfect. Okay. And it's fairly complicated expressions at least. It handled nested expressions and all kinds of stuff. So I said, okay, can you write me a program to translate that? Pretty simple HTML. And kept writing programs that didn't convert the mathematics to LaTeX, even though it did that when I asked it to. And I spent over a day's work going back and forth with the AI. And then finally, the AI said, what wasn't like this? The AI expressed itself very well. It said, oh, you mean you wanted me to parse those things? Well, that's a different story. And that's a different level of programming. I said, yeah, I tried to do a parser. And I got it to pretty much work as long as I put the delimiters in. I don't want to be bothered with putting the delimiters for the math expressions of them because it's error prone and it causes errors that I've got to debug, which is what takes all the time. And I'm not good with clerical stuff, although I can do what I'm saying pretty accurately. Can I do it with a list of 1,000 problems without causing bugs that are going to take me hours to code? So just the lesson being then, then I asked it to do another program I really needed, which didn't involve parsing, and boom, a couple of iterations. And I had it, and I'm really glad to have that one. There's another one I'm going to ask it to do. And I know it's going to do that well because it doesn't involve parsing. But the thing is, something that the AI can do easily, if I give it those 1,000 problems, it would take it a while. Okay? It might take it an hour. But it would be able to do it, and it would pretty much be right. And then I assumed that I could ask it to write a program to do that. And that's where it went wrong. I assumed that something it could do easily, we could write a program for easily. And I see right now just how ignorant that assumption was. And if I'd have thought about it, I might have avoided it. Okay, well, just an anecdote about AI. Okay. So next thing I want to talk about is just little geometry. Pretty easy. Now, you know that if light hits the water, it gets refracted, right? So when you're out trying to get dinner by spearfishing or using a bow and arrow, you got to either aim low or high, which is it? You don't look like you're starving. Yeah, you got to aim low. Okay. And that's because of the refraction. Okay. So you're familiar with the idea of refraction. When you look at something under the water, it's not where it looks like it is. Okay. The reason for that is, anybody know the reason for that? I mean, there's a rule for it, but that's not a reason. The reason is that light moves slower in water than it moves in air. And we'll make that connection, but that's the basic principle. That along with Huygens principle, Huygens, however, that's it's a Dutch name, and they don't pronounce other languages well at all. Okay. So what we're going to look at first, and this is kind of the pinnacle. Okay. And we're going to look at this in lab. Now, this is supposed to be a circle, but it represents a cylinder. It could represent this cylinder, but this isn't really a cylinder. And it's got to be round, so I'm probably going to use a soft drink bottle if I can find my soft drink bottles. It'll be next year before I get everything intact. It's an ADA. Got to be the priority. Hopefully I'll find everything I need before lab. Okay, so here we've got a cylindrical chunk of water, okay? Or if you like, a big old 2-liter cylindrical diamond. That would be interesting, but that's expensive. Okay, I found very few diamonds of that size in my property. Okay, so now we have a bunch of light coming in. These represent light rays, and we'll talk about what light rays really are, but okay. It's like light from the sun, which is what we're actually going to look at. So we're going to look at today or Wednesday, because I don't know how much sun there's supposed to be Friday. Okay, we got light coming from the sun. Let's just say that this thing is oriented so its axis is perpendicular to the direction from the sun. Just to make it simple. It's a lot more interesting when it isn't perpendicular because you get a really neat shape that's neat to try to analyze. But anyhow, okay, you got light coming from the sun. Now, what happens to the light? Well, first of all, here's the center. We'll say this ray is going through the center. Okay? So this ray goes through the center and is undeflected. Why is it undeflected? Because it hits this first face at a perpendicular. And if I'd have drawn this circle a little better, it would show up better. But it hits the second face at a perpendicular. So we got right angles here and here. And if you've got a right angle, the fact that the ray, well, we'll say in a minute. Okay. Anyhow, you got a right angle, so it's undeflected. I'll tell you why this one is deflected, so you can see why this one isn't. Okay, so this ray just above the center, this ray comes in, it comes here, and now it's hitting at an angle. Now, if you look at the center ray and this ray, you see that they hit at almost the same time. There isn't much difference in how far this one has to go than this one before it hits the cylinder because you're pretty close to the axis of the cylinder. You're pretty close to the center of the cylinder. And there's just not much difference in that distance. Okay, well, what happens though is that then due to the fact that this ray moves more slowly through the material than this ray, I don't want to go through details of making that connection. It gets refracted. That means it changes its direction. So that its direction goes more like so, and it hits the back of the cylinder. Okay. Then this ray hits at an even bigger angle. So it deviates from its original direction by even more. And it hits the back of the cylinder. That's not going to cross paths with the other two deflected ray. The other deflected ray starts higher and it's going to stay higher in this picture. And the similar thing happens underneath. Okay. Now, when these two rays hit the back of the cylinder, they aren't going to get deflected by a whole lot, but they're going to be deflected back toward their original direction, but not all the way back to the original direction. And they're going to pass through here. So then this one pass through maybe like so. Now, if these rays are closer to the center than I've made them, then they're all going to cross at about the same point. That didn't come out well when I wrote it, but it reads focal point. Now, in reality, I don't want to talk about radial lines and angles at this point. In reality, if this top ray was as far from the center ray relative to the radius of the cylinder, if it was as far as I've pictured it, it's not going to hit right at the same point where the other two rays do. There's going to be some confusion there, okay? Which means you're going to get a distorted image. This is a problem. I was at a physics meeting in Richmond decades ago with a laser pointer. And it was dinner. There were these glasses, and I was pointing the laser pointer at the glasses and observing how the dot I saw on the front of the glass compared to the position of the dot in the back, and when I moved them, how did they move and stuff like that. So I worked this thing out in my head on the drive back. I had just enough working memory to do it right. It took me several tries. It took me probably an hour and a half to think it through. But probably going to show you that if we have time. It's kind of interesting. And then you can think about the multivariable calculus of the shape that forms when the sunlight hits this vertical sphere at this angle, and you look at a flat screen on the other side of the bottle, and you get this interesting shape. I've never actually worked that out because you really kind of have to do it using a computer and stuff. Just I know what to do. So as far as I'm concerned, the problem is, but it'd be kind of neat to do it. Might just get AI to write me a program for that, because that one's just a lot of detail. Be an easy program to write. Uh, I don't think I have time. Okay, now let's say that I take this sphere or the cylinder and shave off just this little section. Then I have what I call a thin lens, a thin spherical lens. Okay. Single convex, meaning it's convex only on one side. Okay. But really what I want works a little better is a double convex. So here's the geometry of the situation. The central axis here, and I have some object over here that I want to form an image of. Okay, let this be a candle. And you got a candle flame. And you want to form an image of that candle flame on the other side of this central axis. We can actually do that. I have candles, I have lenses, and I have matches. Unfortunately, we can't do it all that well because when this lab was designed and rewired and we got new lights and everything's beautiful and wonderful. And I really like the renovation. I don't like what I had to do, unpack the lab, repack it, and try to get it all back together while doing everything else. I accept it. I just would rather I didn't have to do that while I'm doing ADA. Okay, so it's got me stressed, not stressed, just got to have some sacrifices of time, which is why I can't always find everything. No excuse. I've got that stuff, so I'm probably going to do some of that Friday. The problem is they put a permanent light right here. You can't turn it off. We need it dark to do any good optics. So we're somewhat constrained. Anyhow, we do have lasers and, lasers are all right with the light. Not really, because there's some things we need to do that we can't, but that's it. Okay, so there we have it. Candle, lens, central axis. Now, light from the candle, it goes parallel to the central axis, gets refracted, through a focal point at distance f from the thin lens. Now I should have put the lens a little further from the candle. That's okay. Now, another light ray I kind of cheated. I curved these a little bit. Another light ray goes through the center of the lens and eventually intersects the refracted ray that went in parallel to the central axis. And that's where the image of the tip of the candle forms. Now, another ray goes through the focal point on this side, hits the lens. If the lens is big enough, I didn't make the lens big enough to draw it, and that's why I wish I'd put these a little further apart. But anyhow, there's another ray, a third ray that you can see in the introductory problem sets. I've got good diagrams in them. Okay. And it also intersects here. And so do all the other rays that come from the tip of the candle flame. to make the statement that all rays from the tip of the candle flame ideally intersect, converge at this point. Well, there's the tip of the candle flame. The same happens for the rest of the candle flame. And assume you have a glowing you get the whole upside down image. And if you get it dark enough, you can hold a screen right here and see that image. Nobody asked me if it was a good idea to have a permanent light in this room. And if I'd have been in their position and whatnot, the physics, I wouldn't have thought to ask you. Okay. Although maybe I'd have had a meeting. They might have had a meeting about the design of the room. Okay. So I'm not throwing any stones. It's just inconvenient that we got that light. Also inconvenient, we got a heating system we can't turn off. So we've always got air moving in here. Things that we'd like to be able to do. And technically it's possible, but it's pretty inconvenient for our building and grounds people. Turn that off. It messes other things up. So we probably can't do that. Okay, anyhow, that's basic geometry of image formation. So I want you to take that geometry to the last 3 or 4 problems in the waves set, which talk about optics. Okay, at this level, this is a pretty simple level. This is really high school level. Okay, but we want to get it right because in high school people can't do the geometry anymore. You have a lot of similar triangles that occur here, and you use those similar triangles in analyzing what goes on. And they're lenses that diverge. You have a convex lens, you have concave lenses that cause things to diverge. And what happens there? And then what happens if you look into a reflecting sphere? You see strange, distorted picture of whatever's in the vicinity. It just comes out from, you trace the rays and see how they form images, virtual images, and all that stuff. Okay, so I want you to familiarize yourself pretty well with those last 4 problems. And then we can talk more about it. Okay, related to the bringing aluminum rods. Question we're going to answer by doing it in lab, but I want you to come in knowing what you're going to do. Here's an aluminum rod. And if I hold it close enough to the center, if I can find it, come on. Okay, that's probably pretty good. I can make it sound. I hit it on the end. A high pitched sound. Wherever my microphone is, I think it's over there. As I rotate it, also there's some Doppler effect, can't you? Higher and lower. Sounds higher. It sounds low. Now, what I want to do in the lab is think about the standing waves you can get in this. you know something about standing waves in a rubber band chain, okay? There are places where I can support this thing and it'll ring at a different frequency, higher frequency. So you want to get the idea of that. Now, this. You ever heard the song? Na 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 na. Hey hey hey, goodbye. Na 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 na. Hey hey hey, goodbye. How many have heard that song? Okay. Yeah, yeah. Well, that was around when I was in college. It was a good song. We liked it. Okay. Uh, what's that have to do with the vibrations or the harmonics of the rubber band or the rubber band chain? Okay, now, if this represents the rubber band chain, where we were moving the rubber band just a little bit at the ends, but it moved much more at the middle. So essentially at the end, we had a node. And that's at each end, unless one of our participants, who's not here today, that at Virginia Tech giving them heck. Okay. Uh, so he's away for good reason and emailed me well in advance telling me this. Uh, how many peaks would you see in this wave? What would it look like? Did you see anything like this when we were doing the experiment with the rubber band chain out in the hall? How many peaks would there be? So four, yeah, four. Here, 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 and here. The antinodes are the peaks. So your chain would look like would look kind of like this. I don't have it quite as regular as it ought to be. You get the idea. And how does this occur? This occurs when there's effectively a wave moving from this end. This is equivalent, let's say, if you have a wave moving in this direction from this end with the same node antinode spacing, and another wave moving at the same speed from the opposite direction. Okay. Now, ideally, if I'd have been thinking, I would have made the amplitudes of these waves moving from the left and moving from the right half as great as the amplitude of the resultant wave. Instead, I'm going to correct my picture by improving the actual wave. Let's say, okay, node here, antinode here, node here, antinode here. The axis of symmetry. And now Each of these waves has an amplitude. Each of the virtual waves, the imaginary waves, has an amplitude that's half the amplitude of what I've drawn in here, right? And then, of course, what you're really seeing is your eye picks up something that looks like this, right? The thing's oscillating very fast. You're just going to see the envelope of these waves. But what's happening is, and I've said it in previous class, hopefully you processed it, as these waves move across each other, sometimes their peaks reinforce, sometimes they cancel. So what's going to happen is you go from like here where the peaks are reinforcing, and then maybe here where they're 45 degrees out of phase, and here where they cancel. I'll actually go ahead and so it's here, then 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 it goes back. So we're just kind of, well, it's actually just doing this at this point. The envelope, which is the set of points that approaches or doesn't pass, okay? Or reaches and doesn't pass, is this thing that you see, okay? Now, if I know how fast the wave is propagating, and if I know the distance between a node and an antinode, I can figure out what? I can figure out the frequency of this wave. Because I know the distance between a node and an antinode, that's 1/4 of a complete cycle, isn't it? Okay. Well, that's all I need to know to figure out the harmonics that'll occur in the rubber band. It's another filter. Just insert it in this little box here. And a nano. Nano. This is and a nano. Okay. This corresponds to the ends being free to move. If I hold this rod at the middle and clank it at the end with something hard, my knuckles aren't going to do it, and I'm not at the middle anyway. I want you to see, okay? Then this end is free to oscillate in this direction. Make sense? Yeah. Okay. If I hit it on this end, then that sends a compression wave down toward the other end. That compression wave contains an infinite number, an essentially infinite number of frequencies. Okay. Only the frequencies that correspond to wavelengths that match up with the length of the rod. And those wavelengths would be the wavelengths you get from ANA, or from ANA, or from ANA, etc. Because these are compression waves moving along the axis of the rod, moving parallel to the axis of the rod, and they cause the rod at this end to vibrate like this. You can tell, just to get a good one going and just touch the end, you'll damp it out. But if there's also a transverse wave going on, okay, this is called longitudinal. This one is called transverse. Yeah, it was in the middle of a sentence. I forgot what the sentence was, but I was talking about if you got A and A, then what's the wavelength of the wave? If the length of the rod is just that, if that's the whole length of the rod, then what's the wavelength? It's twice the length of the rod. Because a full wavelength is 4/4 waves. Between an A and an N is 1/4 of a wave. Just think here, here's your wavelength. You got 4/4 waves in that length. Convince yourself of that. Make sure you really understand that. That's fundamental. You can use the formulas without understanding that, but you don't know any physics if all you can do is use the formulas. Incidentally, y'all were thinking well with physics when we talked about the thermodynamic thing. Okay. You didn't have all the details, but tell you'd been looking at it and thinking about it and stuff. And conceptual stuff was looking pretty good. We want to get the same conceptual level with this system. Okay. If you got this one, that means that the length of the rod would be one full wavelength. If the length of the rod is a full wavelength, then the frequency of the vibration you hear is that, well, of this wavelength, okay? The more of these you get, the shorter the wavelength, okay? If you have this, then the length of the rod is half the length, is half a wavelength, so wavelength is twice the length of the rod. If you have this oscillation, then the length of the rod is the length of the wavelength. If you have this one, then the length of the rod is 2/3. That is 3/2 of a wavelength. So that the frequency is 2/3 of previous. And you get this sequence of frequencies that you need to read about and learn about. Okay, well, we're out of time. Try to digest that and relate it to what you see in the problem sets. And, also you ought to be scanning through your text on waves and just, scan through and say, oh, shoot, I don't know anything about that, but there's something that's familiar, and try to begin to get a picture of how all this stuff hangs together. Look at the chapter summary. You're going to see a lot of the same stuff you see in the introductory problem sets. You got to see some stuff you don't see because you're sacrificing a little bit of material to the weather. Okay.